As of late December 2025, 3I Atlas is already moving away from the inner solar system. It has passed Earth's closest approach, and no spacecraft is following it. What remains is only data, and some of it does not behave the way it should. The strange signals did not appear in visible light, but in deeper wavelengths. As those signals emerged, scientific explanations became unusually careful. But what exactly are those signals, and why do they break the standard comet models? The most unexpected shift in the story of 3I Atlas did not come from sharper images, but from a completely different part of the electromagnetic spectrum. Observations from ESA's XMM Newton and the X-RISM mission operated by JAXA and NASA revealed extended X-ray emission stretching hundreds of thousands of miles away from the object. This was not reflected sunlight. It was high-energy radiation produced by interactions between ionized gas surrounding Atlas and the solar wind itself. X-ray emission from comets is not entirely unknown, but it usually follows a predictable pattern driven by charge exchange interactions between neutral gases and fast solar particles. In the case of 3I Atlas, however, the intensity, spatial extent, and timing of the emission did not line up cleanly with those expectations. The X-ray glow appeared more persistent and more structured than models built from solar system comets would predict, suggesting a plasma environment that was being energized in a different way. Spectral analysis added another layer of complexity. The X-ray data revealed signatures consistent with elements such as carbon, nitrogen, and oxygen, indicating that the surrounding coma was not simply passive debris, but an active, evolving plasma shaped by electromagnetic forces. These observations imply that Atlas was not only losing material, but was dynamically interacting with solar radiation and magnetic fields, creating a measurable footprint far beyond what visible observations alone could show. What makes this evidence particularly important is that it challenges a core assumption in comet science that activity scales primarily with heat. In Atlas's case, energetic interactions appeared where thermal models predicted relative calm. To make the equations work, researchers would have to stretch density estimates, composition, ratios, or plasma coupling efficiencies beyond their usual ranges. The physics still holds, but only just. If X-ray and plasma interactions dominate the observed behavior, what do they reveal about the true material nature of 3I Atlas? When 3I Atlas reached its closest approach to Earth on December 19, 2025, ground-based telescopes captured a feature that immediately stood out: an anti-tail. Instead of pointing away from the sun like a normal comet tail, this structure appeared to extend sunward, defying the most basic visual expectation of comet behavior. While anti-tails have been observed in rare cases before, they are typically brief projection effects tied to viewing geometry. Atlas did not fit that pattern cleanly. The structure appeared well-defined and persistent across multiple observing windows, suggesting that geometry alone was not sufficient to explain it. This raised the possibility that dust and gas were being released in a highly directional way, potentially aligned with the object's rotation axis rather than evenly distributed across its surface. If true, this would imply a nucleus with strong compositional or structural asymmetry, where certain regions dominate activity regardless of solar heating. Another explanation points back to the plasma environment identified in the X-ray data. Charged dust grains and ionized gas do not always follow simple ballistic trajectories. Under the influence of solar magnetic fields and the solar wind, these particles can be redirected in ways that visually contradict classical tail models. In this scenario, the anti-tail is not pointing toward the sun because material is falling inward, but because electromagnetic forces are reshaping the outflow after it leaves the nucleus. Additional context came from instruments associated with ESA's JUICE mission, which recorded complementary imaging and spectral data during the same period. While JUICE was not designed to study interstellar objects, its measurements added independent confirmation that the region surrounding Atlas was dynamically active, with dust, gas, and plasma interacting in a more complex configuration than standard cometary envelopes. Taken together, the optical antitail, the directional outgassing hypotheses, and the plasma-driven restructuring all point in the same direction. 3I Atlas was not behaving like a uniformly heated, symmetric body. Its activity appeared shaped by internal structure, rotation, and electromagnetic forces acting together, rather than by sunlight alone. Do the antitail and these unusual structures reflect a patchwork composition inherited from another star system? Or do they point to a physical mechanism we have not yet learned how to model properly? Ultraviolet and infrared observations added a critical layer to the story by probing what 3I Atlas was actually made of. Data reported in recent preprints on RxIve revealed signatures consistent with water and carbon dioxide within the coma. While the presence of water is expected for comet-like bodies, the relative dominance of carbon dioxide stood out immediately. Compared to most solar system comets, Atlas appeared unusually rich in carbon dioxide-driven activity. This matters because carbon dioxide behaves very differently from water ice. It can sublimate at much lower solar heating levels, allowing outgassing to begin far from the sun, where thermal models would normally predict only weak or negligible activity. In other words, Atlas did not need to be warm to be active. This helps explain why strong outgassing and energetic interactions were observed at distances where typical comets remain comparatively quiet. The elevated carbon dioxide fraction also hints at a very different formation environment. In our solar system, repeated passes near the sun tend to deplete the most volatile ices first. An object that still retains large reservoirs of carbon dioxide likely formed and remained in a colder, darker stellar system, where radiation levels and thermal cycling followed a different evolutionary path. Atlas appears less processed, preserving a chemical memory of conditions beyond our sun's influence. These compositional clues reinforce earlier observations of sustained activity that did not track cleanly with distance from the sun. Instead of turning on and off according to simple heating curves, Atlas behaved as though its internal chemistry was setting the pace. Outgassing became a function of volatile availability and structural pathways within the nucleus, rather than surface temperature alone. Taken together, the chemistry suggests that 3I Atlas may not fit comfortably into the category of a cold, inert interstellar rock. Its behavior is more consistent with a volatile-rich fragment, actively releasing material under conditions that challenge long-standing assumptions about how cometary activity should scale. Does this volatile-rich chemistry mean that 3I Atlas is fundamentally different from ordinary comets? Or does it reveal a broader class of interstellar objects we have simply never had the chance to observe before? "3I Atlas has already passed its closest approach to Earth at a safe distance of roughly 1.7 to 1.8 astronomical units, and it is now steadily leaving the inner solar system. With every passing week, it grows fainter, colder, and harder to observe. After December 2025, the window for detailed study narrows rapidly, and much of what it carried through our system will never be accessible again. According to reporting from Live Science, this encounter was brief by cosmic standards and unforgiving in what it allowed us to miss. What remains is not the object itself, but the consequences of its passage. The data gathered during this short interval have already begun to strain existing models of cometary physics, plasma interaction, and volatile-driven activity. That tension has reignited a serious debate within the scientific community whether future interstellar visitors should be met with dedicated interception missions, designed not just to observe, but to directly sample material formed around other stars. Atlas has made one thing clear: passive observation may no longer be enough. At the same time, it is important to be precise about what the data do not show. Extensive searches conducted by Breakthrough Listen, in coordination with SETI Institute efforts, have found no evidence of artificial radio transmissions associated with 3I Atlas. Every signal detected so far is consistent with natural physical processes. The mystery here is not technological, it is astrophysical, and that distinction matters. Atlas does not demand extraordinary explanations. What it demands is better physics. It forces researchers to confront how little we truly know about material formed beyond our solar system, shaped by unfamiliar radiation environments, different thermal histories, and plasma conditions we have never directly sampled. In that sense, its greatest impact is not what it was, but what it exposed: the limits of models built almost entirely from local experience. 3I Atlas is already fading into interstellar darkness, but the questions it left behind will not fade with it. They will shape how the next interstellar object is recognized, prioritized, and understood. Is 3I Atlas merely an unusual visitor from another star system, or the first clear signal that interstellar astronomy is entering an entirely new era?